So then let's just continue in the last 3 hours or the first 3 hours. And I gave you an introduction, and now we will continue with this introduction by using such diagrams. Yeah? So I showed you last time so here we have again the Earth surface with the house, and below the Earth surface we have some intrusion which are coming very shallow or very close to the Earth surface, yeah? And we were talking about granitic intrusions and some others becoming more stuck, or they become stuck in the lower crust at a depth of about 15 kilometers, yeah? And the reason was, I told you these shallow intrusions coming more to the Earth's surface because this melt has been more hot, yeah? And if a melt is hot, then the fluid concentration is lower. You know this by now, yeah? And if the melt is hot and the fluid concentration is lower, then the melt is more SiO2 rich, yeah? That is the situation here, and the viscosity of our melt, if the melt is more rich in silica, that means the viscosity is also lower. Yeah? So if you remember, or if you are checking on your water tank, the water, then the viscosity of water is 1. Yeah? From such melts, it even can be below 1. So they are very mobile. Whereas if we have a magma or a melt which becomes stuck more deep in the lower crust, then this melt has a lower SiO2 concentration. If the SiO2 concentration is lower, then the viscosity is higher. The temperature of this melt while it crystallizes is lower, and the density is also then higher. So this is a higher dense melt, this is a lower dense melt. So and now regarding our ore deposits, yeah? I told you last week, or just on Wednesday, that certain elements to form the ore deposit becomes enriched in certain melts. So and here we are checking now these granitic melts, these felsic melts. So and then we have here this diagram. On this, here we have the logarithm of the ionic potential. So in the ionic potential that is just, you are using the charge. Yeah, you know how many electrons in the outermost rim, yeah? You can just check it in your periodic table. Then it is written, for example, copper has 2 electrons in the outermost rim. Magnesium has 2 electrons in the outermost rim, whereas, for example, aluminium has 3 electrons in the outermost rim, or lanthan, yeah. Iron can have 2 or 3, depends on the stage of oxidation. So, and then you have the radius. So, in the radius of every element you can also find in the periodic table, yeah. So in there we have bigger elements and smaller elements. So if you are using just a charge and dividing it by the radius, then you get this ionic potential. So that is a very simple mathematical calculation. So and here the authors have used the log. So and that means you have just to press on your calculator the log button, yeah? And then you get these values. So and here they have plotted it against the ionic radius, and the ionic radius you can also find, as I told you before, on the periodic table. So and then we have here on this side elements with a very high charge, 6 electrons in the outermost rim, 4, 5, 4, 3, 2, 1. So in these elements, with these high charged elements, we are calling the lithophile elements. And these lower charged elements, we are calling the chalcophile elements. So in all these elements can be found in a certain place of your intrusion. Yeah? That's now the important thing for you as a geologist. Here, for example, I think we have silver, gold, then we have here magnesium, cadmium, then we have here iron, here we have some cobalt, and here we have the high charged lithophile elements like molybdenum and wolfram. So, and these are just textbook diagrams. So, but then here, that is now the interesting thing for you as the geologist. The chalcophile elements, they become enriched in the country box. So, and if we are going back to our simple sketch here, yep. Then all these surrounding rocks here these are the country rocks, yeah? These are these rocks where our granitic melt becomes in place, yeah? So if you are looking, for example, now for molybdenum, yeah? Then it is the typical site of the deposition that is here in the Pluto, yeah? So the molybdenum and the wolfram you will mainly find here in the contact metamorphic zone, yeah? So, but if we are going here and you are looking for copper and gold, then you will find them in the country rocks, yeah? That is somewhere here. So then the next thing is the most composition of the Pluton, yeah? On this side we have a silica-rich Pluton. On this side we have a calc-alkaline-rich Pluton. So the calc-alkaline-rich Pluton is this one, yeah? The silica-rich Pluton is this one. So and now for us also a very important thing, the root or source of the formation. We have here magmatic, and then we have a pneumalitic zone, and here we have a hydrothermal zone, yeah? So certain elements or certain ore deposits are pure magmatic, yeah? You will see this later what means pure magmatic. So and the others are hydrothermal. And the hydrothermal ore deposits, these are chalcophile ore deposits and they are hydrothermal. And here we have our gold and our copper. So and this gold and this copper, I told you this also before. They are enriched in such veinlets, yeah? Maybe we should use another pen. They are enriched in these veinlets. So in these veinlets, these are veins, and that is just written here, yeah? So and this is the hydrothermal stage, and then you will find your copper and your gold in these veinlets, and there you can mine it, and these veinlets are maybe, they can be up in diameter 10 centimeter, but most of them are even smaller. So here we have the deposit type, here we have pegmatites, and here we have the veins. So the pegmatitic stage, that is at about 600 degrees Celsius, and the hydrothermal stage is then below 500 degrees Celsius. So then the age of the formation, this stuff that is formed very early, at the beginning when your Pluton takes place. So in these veinlets, in the hydrothermal stage, that is late. So why is this late? I mean, at first we have here the emplacement of such a Pluton, and if this Pluton is a more cool Pluton, yeah, becomes stuck in the lower crust, then it's maybe 750 to 800 degrees hot. So in these veinlets, you are forming them at a temperature of about 500 degrees Celsius and lower. So the whole thing has to become cooled down, yeah? So, and I told you this before, your Pluton will crystallize from outside to inside. Then you have at some stage your residual melt. So and this residual melt becomes then always more and more enriched in water. The pressure becomes higher, yeah? Because of the extension of the water molecules, yeah? They need space, and then it just shoots out in such veins. So now, here we have the minerals, here are oxides, yeah? So, and here the minerals which you will find, these are sulfides. And we will show them in the practical, the sulfides, yeah? I mean, if you are looking for a copper or shell, then we will also find a lot of ions, yeah? Whereas if we have here in a Pluton, you will not find then any oxides, yeah? So, and these then are all fingerprints to identify a certain ore deposit, yeah? So and now we have here the next button here, dealing about fluoride hydroxide on complexes. We have here fluid transport, these are carbonate complexes. These carbonate complexes will not occur here in the surrounding veinlets. Here again the temperature, we have here a higher temperature because that the emplacement of such an ore deposit takes place at higher temperatures. And here we have the low temperature situation. Then the level of emplacement, here we have a deep level, and here we have a shallow level. What we can find here, a deep level and a shallow level. So we will then upload all these diagrams. So here is another diagram how these wavelets are looking with depth. We are going here from the Earth's surface down to 24,000 meter, yeah? So, and this is now here we have everywhere the emplacement of our Pluto. Here at the shallow depth we have only a few veins and bigger veins. If we are going more deep, here let us say we have here 6,000 meter, then we are forming here more veins and longer veins. So, and if you are going here to a depth of 16,000 meter, then we are forming such patches. So here as well. That means we are forming at a certain depth, we are forming a certain ore deposit. Yeah? It is not only related on the temperature of your granite and that. I mean, of course, the shadow emplacement of such a Pluto takes place at higher temperatures, where the more deep intrusion takes place at lower temperatures. We know this by now. But we will then find at a certain depth certain ore deposits. So here, for example, at very shallow depth, we can form tin deposits, yeah? So, and these tin deposits are associated with cassiterite erz and with sulfides, yeah? So, and I don't know, we went at the ES301 field trip, we went to this core sheet in Mandy, is it? So yes, and they have done this drill course for copper exploration, yeah? So a little bit, and here you have then the associated minerals. So here we have also tin deposits, but here we are forming then these rhizons as well. So, and here we have then also some other minerals inside, tantalites we have inside. And we are forming here then these quartz-rich veins. So if we are going to this type of intrusion, yeah, that is a little bit stupid because the table is too small. Then we are finding here some muscovite inside and some amphibolites. So that means if you are going there around here, somewhere here, and you are looking for a gold core deposit, yeah, then if you can identify some muscovite, then you know that was a very deep granitic intrusion, yeah? And then in such deep granitic intrusions, you can then, these are bismarcks, yeah? So in this granitic intrusion, has taken place in a depth of 20,000 meter, yeah? So, and then you have formed later on these wavelets, yeah? In the hydrothermal stage. So, but now the thing is, that is now a textural thing. this here and this here are not longer wavelets. These are just patches, yeah? So, but at more shallow depth you have the wavelets. So, and that is now also a very important thing for you as a miner, if you have to look for wavelets or only for these patches. So, because it changes then the mining technology, yeah? So what you as a ES301 student should now have in mind is that you are forming this, from a granite you can form different ore deposits, and this different ore deposit has been formed at a different depth from a different melt. Yeah? And there you can then enrich certain elements and can form an ore deposit, and that I showed you just before. So now we have here written something about tin ore deposits. And this is now here a tin ore deposit, or it's not, it's only a diagram. So, and these are ore deposits where you can find tin, you can find wolfram, molybdenum, and beryllium. If you are looking then for your tin ore deposit, then you are not running around with an hand dance on the ground and looking for tin, yeah? Because that is too exhausting. But you are looking for rocks or pegmatites which show a certain a certain mineralogy. So here on this side they have subdivided this in polymineralisch and here in monomineralisch. So in these monomineralisch ore deposits, these are then these ultra grisons, and the other ones are just the grisons, yeah? So and in our first hour, I told you what a grison is, yeah? And it is also written in the manuscript, which we will load up this weekend or maybe still today, yeah? So, you can have here in this polymineralic tin, wolfram, molybdenum, and beryllium ore deposit, you can have the mineral assemblage quartz topaz, quartz mica, quartz tourmaline, topaz mica, quartz fluorite. So, and if you can find this mineralogy, and I mean a quartz, you can identify very easily, yeah? So in the topaz, you can then identify very easily the tourmaline, that is very, very easy. It's this greenish mineral which shows this shape along the 001 axis. So then the mica, you know also, here also mica is very easy, yeah? I think we have here such a rock sample. I don't know where it is, but we will show it to you in the record. Yeah? There is somewhere a muscovite together with quartz. So, or you have three minerals, a mineral assemblage or paragenes consists of quartz, topaz, and mica, or quartz, mica, and fluorite. So, in this you can identify very easily in the field and basically, yeah? So, and then you know, if you can find this mineral assemblage, then it is a good candidate to find tin, wolfram, molybdenum, and beryllium. Or you have these monomineralic compositions containing only quartz, topaz, mica, or tourmaline. So, and these micas can then be subdivided. So that is then the next step. You find some mica, yeah? So, and then you know from the ES301 class, we have d-octaedric micas and we have 3-octaedric micas, yeah? So, and then you know this, the d-octaedric mica, that is the muscovite and that is the silver shining one, yeah? Whereas the 3-octaedric mica, that is the biotite, yeah? So, and then you can, then you have the zinwaldite, that is then just a mica containing some tin inside. Then you have a proto-lithiumite, that is then, if you have lithium inside, it's also a very good indicator if you are looking for lithium. And if you are looking for lithium, then you will, and you will find lithium, then you are a rich man, because lithium is very important for the handies, yeah? So, and there an indicator is this kind of mica. Then you have the muscovite, you know this by now as the silver shining one. And the sericite. So, in the sericite is formed under different PT conditions, for example, compared to the muscovite. And the biotite is also formed at different PT conditions and at different whole compositions, yeah? Because if you are forming a biotite, then your melt was more rich in magnesium and iron. If you are forming a muscovite, then your melt has been more enriched in aluminium. The other thing is, if you have muscovite, then your melt was a more water-rich melt, yeah? So, and then you can produce more melt, and you have more volatiles. And you will then form a different ore deposit compared to those containing, for example, a biotite, yeah? So, because a melt which contains biotite has a lower water concentration, therefore it was more hot, therefore it intruded in a more shallow depth, yeah? Whereas if you have a melt containing muscovite, it was a cooler melt and intruded more deep in the lower crust, yeah? And therefore you will then find other ore minerals compared to those melt, which is formed more in a shallow depth, yeah? But to make here some calculations, and we will do it one time in the practical using a computer program. If you are doing this calculation, then you need mineral chemical analysis. I mean, of course, you can seal them, or you can separate a muscovite in the hand specimen from a biotite. Yeah, that's not a problem. The other one is black and the other one is silver. Yeah. So, and then you can make, by using such textbook diagrams, more precisely estimations of the depth that such an intrusion or a melt takes place, yeah? And if you have a depth, then you can make more estimations about the composition of the melt. And if you have then the depth and the composition of the melt, then you can also make a more precise estimation what type of ore minerals you will find. So, and that is very important because all this exploration work costs a lot of money. So, and if you remember at the ES301 people, you saw the core shed, and then they have taken 253 cores, and then there was no copper ore deposit. So, and I mean, how much is 1 meter? 1 meter drilling is 200 Australian dollar. That is in Fijian dollar, $250. 300. So and they drill down to a depth of about 600 meters, yeah? And then they have done 250 times to discover that there is no copper ore deposit. So and then it was actually not a big business. So and therefore we are doing all these jokes here, yeah? That is not only for academic games. So then we have here another table. I have just to make it a little bit smaller. So here we have a table which shows us the summation around such a Kreisel. Yeah? That is, I mean, the Kreisel is this part where it becomes heated up. Yeah? So that is then a contact metamorphic zone. Yeah? So and then we have the original rock where the original country rock, yeah? So in the original country rock, that is this one here, yeah? So the glycinitized rock, that is this one, yeah? So that is this part of the contact zone between the granitic melt and the alumosilicate rich rock. So and here, our melt takes place in alumosilicate rock, or in a carbonate rock, or in mafic and ultramafic rock units. And then we can just check here we will produce then such a glycinized rock. Here we will produce a fluoritized limestone, and here we will produce serpentine and talc. So and therefore the minerals which we will find then in this zone are different, yeah? Because here in the first stage here we have just heated up alumosilicates, yeah? So and if we have here this intrusion or the intrusion which takes place, then you know by now as well, because I'm always spraying this and draining this, that there is fluid coming out, yeah? Otherwise you cannot produce these veins. So and this fluid is shooting out and is doing then something with your surrounding country rock, yeah? So and then it depends on the chemistry from the country rock. Because if here fluid comes out and is shooting here in this surrounding country rock, with a rock which was before an alumosilicate, then, I mean, here is written alumosilicate, and you know the most common alumosilicates by now. That is the kyanite, the sillimanite, and the andalusite. You know it from last semester because you did this calculation with me. So, and then you have in this alumosilicate rich rock, you have also some other minerals inside, but you have aluminium and you have silica. because it's just written here, yeah? So, and if such aluminosilicates undergoes metamorphism, then you will produce metamorphic minerals which contains aluminium and silicate, yeah? So, and the volatiles which shooting out are mainly water and CO2. So that means you will produce in your bison a water-bearing mineral, yeah? Because you are adding to your alumosilicate water, and what happens? You will then produce a mica. So, and then you have also your quartz inside, and you will produce here in your bison, you will produce quartz and mica directly in the contact zone, yeah? So, and in such an ore deposit where you have then quartz and mica, you will find then other ore minerals compared to the other three, yeah? Because the chemistry is different, yeah? So if you are going then in a zone more outside, maybe here, then you will produce another stage. You will have quartz, topaz and mica, because the whole thing is cooling down, and if the temperature goes down, then you will produce some other minerals which you can form at lower temperatures, yeah? And in the outermost zone you will form topaz, tourmaline, quartz or mica. I mean topaz or tourmaline or quartz or mica. So and this is all strongly depending on the mineral chemistry. And actually we should, can we not make it during the feature, that we can visit the Cola mine and then taking the boat to Bangla level? Yes, because that would be important, because there in the mine you can see all these zones. You can see it in the hand spacing map. I mean, I have also some pictures here from these zones and I will show it to you, yeah? Otherwise I would not mention it. But there you can see this. I mean, in the Cola mine, the problem is that I can only bring 10 students down, is it? Yes. So in there you can then walk on all your fours here, because it's not that high, yeah? Then you can slippery around here in the depth of 400 meters, it is hot like hell. And there you can see then these zones. It's a good exercise. So that is if our original country rock was made up of aluminosilicates. So if I'm talking now about aluminosilicates, aluminosilicates, these are metamorphic rocks, but what was the precursor from this aluminosilicate? Was it an igneous rock or was it a sedimentary rock? These are meta-sediments. So in such meta-sediments are formed where? At the ocean floor. Because there you have a lot of aluminium, and then you will subduct the whole thing, and then you will form such a metapilite. So and then this metapilite is lying somewhere here around in a depth of I don't know, and then a granitic intrusion comes by, and then you can form these zones. So and then there is another very important thing. Such a shallow intrusion, and I showed you in the diagram before, has taken place in a depth, let us say here, of 20,000 meters. And later on you are forming these wavelets or batches. And the next important thing is, I mean, you have to bring up the whole thing to the Earth's surface, yeah? Or close to the Earth's surface. And therefore you need then some other tectonic processes. So then, now we are having carbonates, yeah? And these are all things which you are looking at, which you can look for here in Fiji. Because you have a lot of carbonates, and you are remember from the ES301 field trip, and also from the ES301 field trip, we saw some huge units of limestones, yeah? So in these limestones has been before carbonates, yeah? But here the limestones, they are not metamorphic rocks. They are still sedimentary rocks. That's also this slightly boundary. But anyway, if your granitic melt intrudes in such carbonates, you will then make a limestone. So in there you have then a lot of CO2-bearing minerals. Yeah? So that means the mineralogy from this horizon is totally different compared to this horizon, yeah? To this one, yeah? Therefore, you will then form in the first stage fluoride. A fluoride is very easy to identify, yeah? Because in your fluid, which was released from your residual melt, or here at the beginning when you are forming your horizon here, contains also some other things inside, like chlorine and fluorine. So, and if you have fluorine, then you can make a calcium fluoride. That is calcium fluoride, and then you have your fluoride crystal. And you can make a tremolite, yeah? The tremolite, that is a water-bearing amphibole. I mean, all amphiboles are water-bearing or has an H2O group, therefore you really need to gain water. But in your carbonates, you have also a lot of calcium inside, of course, and you have magnesium inside. Then you can form a tremolite. So when such a tremolite can be formed at a temperature ranging between 650 and 700 degrees Celsius. So and in a zone more outside, you will have then fluoride, albite and muscovite, yeah? Completely different from this situation here, yeah? So and these are rocks which you can observe, you can sample them, and then you can make first estimations. So and in the outermost zone you have then fluoride and sphassite. So but now here let us include our granitic belt in a more mafic to ultramafic rock unit. So mafic rocks, you know by now, mafic rocks, these are for example gabbros, yeah? And ultramafic rocks, these are all these sersulites, yeah? Which you have found in these rooms in Oregon. So there you have then much more silica undersaturated country rocks, but they contain much more magnesium and iron. So and therefore you will then form a zone here which contains serpentinite and talc. So and this horizon looks then totally different also from the other ones. So then later on you will form a zone of chlorite and actinolite. These are all very water-bearing rich minerals. I mean in the chlorite you have an OH4 group. So and then in the later zone you will then form phlogomite and muscovite, and then margarite and plagioclase. So and this is called then the zoning of such joint controlled horizons, and you can see at least this sequence here you can see here in the Mauda Cola mine. So, but then it depends also on other things. First, it is strongly temperature controlled. Here they may form the Bryson at 450 degrees Celsius, here at 300. There's just a zero missing, or this is a zero, and here we have 200 degrees Celsius. So, and I told you, we have there also chloride inside, yeah? So, and everybody is using chloride of yours every day. So, and when you are using chloride every day, what is this? Salt, yes. And then salt. And here the answer is the salinity, yeah? So it depends also on the salinity of your fluid. So if you like to make some estimations of the salinity of the fluid, you can calculate this. So, but it is you as a human, you are using NaCl, that is chloride for your soup, yeah? And the farmer for the cows is using what? He is using also a salt, but the salt is not that tasty, yeah? That is sylvine, and the sylvine, that is the potassium chloride, yeah? So, but the sylvine is much more cheaper, and cows cannot complain. So that is this one. These are both minerals containing chloride, yeah? And here it is written, potassium divided by sodium. And then you are getting also some estimation of your alkalis inside, yeah? So, and here if you are going down with the temperature, then the salinity decreases. And the potassium to sodium ratio increases. Because sodium, chloride, no, not chloride, salt and sylvine, that means sodium chloride and potassium chloride is formed at lower temperature, yeah? So, and that means the chlorine will go into the crystal lattice and form salt, yeah? So, and therefore the salinity of your fluid goes down because you are removing chloride. Just generally down. So, and then we have something about the molality. So here we have then the activity of potassium divided by the activity of hydrogen. One can use this just by using such tables, or one can calculate it. The activity, that means, as it is written here, the activity, that is how mobile this potassium and this hydrogen is, and of course at higher temperature you have a higher activity because it moves then faster, just in very simple words, yeah? So, and you can do the same here for the sodium. You have the activity of the sodium and the activity of the hydrogen. So we are doing always such ratios, and maybe then in the log loop to create these stability fields, and these stability fields, I will show it to you then, are very important to estimate or to show or find different ore deposits. Because it is not only to find an ore deposit, you also would like to know if this ore deposit is forced to mine or not. Yeah? Because you like to know how many tin is inside in tons. Yeah? If you are looking for diamonds, then you are not looking for tons, you are looking then only for carats. Yeah? It depends always what you like to mine. But that is also a very important thing. Then another very important thing, that is the pH value, and that is then just the activity of your hydrogen atoms. And then you have your different paragenesis at different temperatures. Here, for example, you have muscovite stable in equilibrium with muscovite and albite. Then here you do not have longer albite, you have only muscovite. And here, at 200 degrees Celsius, you have the equilibrium between muscovite and carbonate. Yeah? So what you should have now in mind as a ES301 student, that is ore forming processes, are strongly controlled on the temperature, on the depth, on the salinity, and the pH. Yeah? So, and then under these certain conditions, you will form different minerals, different rock-forming minerals, and in these different rock-forming minerals here at this crescent, you can then form different ore deposits. This is in our way. Another class. So, there I have then the next annoying diagram. Here we have then plotted the logarithm of the activity of the potassium in the fluid, yeah? Because we are using here only the K plus. And here we have the pH. So, and then the whole diagram has been calculated at a temperature of 400 degrees Celsius. You have a pressure of 2.5 kilobars, 2.5 kilobars multiplied by 3.3. Then we have about 8 kilobars. No, we have an F of 8 kilobars. Yeah? Then you have this. Then we have the activity of fluoride, and that is also in the fluid. They have set, that is meter, that is, yes, that is how the activity changes in meter. And here we have it for the sodium. So, and there we have these phase diagrams, and these phase diagrams you can calculate it also by hand, as you have done this last semester. Yeah? The only thing is you are not dealing longer with the pressure and temperature as variables, you are just setting them, and here you have then the parameter of your logarithm of the potassium and your pH value. Yeah? So, and then you have your hand specimen, yeah, because you need then also some connections to the real world. So, and then you can calculate these phase diagrams. Here you have then the stability field of albite, you know, that is a plagioclase. Here of autoclase is the K-feldspar, because here you are increasing the activity of potassium, then you can form a K-feldspar, yeah? So here you have muscovite and quartz, and then you have here talc and quartz. So, and then you know, I mean, if your rock contains albite or autoclase or muscovite and quartz or talc and quartz, you can just see in the hand specimen, yeah? So, and then you can do such calculations, then you know something about the pH, and you know something about the activity of potassium. So, and then you can just go to a table work, and then you can check which ore minerals you can form at a high pH if your rock contains albite and autoclase, yeah? Or at which activity or mobility of the potassium, yeah? So, and that is then fluid dependent, yeah? So, and I showed you in the diagrams before that certain ore minerals are always occurring with certain rock-forming minerals, yeah? So, and I told you before that you are forming certain ore minerals by having a certain fluid, and that is then the composition of the fluid, yeah? Let us just go to the next diagram. This is even more annoying. So, but that is now the reason why we are doing this, yeah? So we have here the mineralogy, 240 degrees Celsius, 320 degrees Celsius, 400 degrees Celsius, yeah? These are always these temperature ranges where you can form hydrothermal ore deposits, yeah? Like copper and gold, yeah? So, and that is the mineralogy in the volume percent, yeah? And I mean you are looking at first we have to look, yes. We have here on the x-axis the fluid, the ratio of the fluid in the granite and the alterated rock. So, and they have done this for 3 stages. F1, that is the fluid composition of the magmatic fluid, and that is the fluid which comes out from your granitic intrusion, yeah? So, and then you have here, that is by weight percent, the fluid of a typical tin granite. So, because we are now looking for a tin ore deposit, yeah? So, and I told you now all the time that we are looking for rock-forming minerals which we can identify in the end specimen. And they have done these diagrams for different temperature steps, 240 degree, 320 degree, 400 degree, yeah? So, and then we have here the mineralogy in volume percent. So, and you have rock containing of quartz, muscovite, carbonite, chlorite, biotite, albite, feldspar. And that is a thing what you can do by yourself, where you don't need a microprobe analyzer or something like this. You can just make a scene section and know how it goes. Maybe you can show it on your example to get the mineralogy in volume percent. Yes, he will show it to you in the practical. So, and then you can count, or you can use programs, you know, like graphic programs, like Photoshop or something like this. And now then you can figure out how many percent quartz is inside, how many percent muscovite, chlorite, feldspar, albite, biotite, yeah? So, and this you can do on your hand specimen, and then you can make first estimation about the temperature when this vein or this rhizome was formed, yeah? Or of course you can use the mineral chemical composition and can make some phase diagrams like iron doing. You can come from both sides. So, and then we have the concentration of the iron in our fluid, that is then just I plotted the logarithm of the mole of divided by kilogram in the fluid. So, but anyway, they have done this for H2 hydrogen, and then they have done it for the total hydrogen amount in the fluid and the total iron amount in the fluid. And you can see the curves are different, yeah? So that means at a certain temperature, we have a higher mobility of the fluid or a lower mobility of the fluid. If we have a higher mobility of the fluid, we can make a bigger ore deposit. So, and therefore the next three diagrams is now important for us because we are looking for a tin ore deposit. So this is the tin. So and if we have, the tin is then not that strongly dependent, or that is the mobility of the tin in the fluid and the wolfram in the fluid. So and if we are increasing the temperature, then our mobility becomes bigger. And now the last diagram, and that is the important one for us, because you as an ore geologist would like to know how many weight % metal is in the rock. So and therefore we are doing this, yeah? So because that is always a very strong factor, how many weight % is inside the rock. So and here they have done this calculation for a tin ore deposit, and I will show you in the practical how to calculate such phase diagrams and how to figure out what is then the weight % of a certain metal in the rock. I think I will do it for the copper. So, and now you will be surprised, here weight % metal in the rock. We are looking for a tin ore deposit, and we have maybe 0.4 weight % of tin is in the rock. Yeah, that's not too much. If we are looking for wolfram, here we have much more. If we are increasing the temperature, then the wolfram peak goes down, the tin peak is nearly the same, but at 400 degrees Celsius, we do not have then the wolfram, but we have a little bit larger field of tin. So, and these can all be calculated by using your rock forming minerals. So, and it is actually a lot of work, but it is for a mining company much cheaper to sit you on a laptop and on a microprobe and do these measurements and do these calculations, as for example the whole geophysical work, which costs a lot of money, and afterwards the drilling. I mean, finally you have to drill, yeah? But in the first stages it is important if you have enriched all these minerals which are more coarse to mine, yeah? That's the point. So, and now we are doing some other stuff, or not some other stuff, that is then all related. But at least we have a picture which does not look that annoying. Yeah? So here we have our granitic intrusion. That is crystallizing of the source granite. Yeah? So, and here we have the isotherm, well, not an isotherm, just an isotherm. 600 degrees Celsius, yeah? And if we have the granite which crystallizes there at 600 degrees Celsius, then it is a more deep intrusion, yeah? I mean, finally, if this granite here is crystallizing as well, then it will also come down at some point to 600 degrees Celsius. Therefore, one has always to be carefully what one is talking about. So, but anyway, we have here 600 degrees Celsius, and the fluid characteristics, that is a magmatic fluid, medium salinity fluid, supercritical, or coexisting with a saltic melt, yeah? I just showed you before in the diagram that the salinity of our melt is very important. And it is supercritical because it's very hot. So, and that is the magmatic fluid, and this magmatic fluid was formed here. And the pressure is lithostatic. That is just driven by the melt source. So here in B, between 500 and 600 degrees, we are running then in the post-magmatic stage. Yeah? The post-magmatic stage means we have here the emplacement of our magmatic melt body, and the post-magmatic stage is the fluid comes now out. Yeah. So, and here we have the high temperature post-magmatic alteration. There we are making our Gleisen and so on. The fluid is magmatic, you have residual salt melt. Yes. So now we are running in stage C. Here we have the boundary C. So in there you can see we are just starting to make our wavelets related to physic alteration, and there we will then start to enrich our tin. Yeah? So the fluid is still mostly magmatic, medium salinity, and some aqueous species in solution. The aqueous species in solution, that is, for example, our potassium and sodium. Yeah? So, and therefore we are calculating the ratio of potassium and sodium, because now we have our alteration zone. The Füllig alteration is a very aluminium-rich zone, but the fluid is still magmatic, has a medium salinity. We can calculate this by using our stuff in the solution. So, and then now we are changing from lithostatic in hydrostatic. In the stage D, we are forming then the wavelets. Yeah? So if we are looking for tin, we are not looking in the wavelets. Yeah? In wavelets, you are looking then for other stuff. Yeah? The fluid is still magmatic, so at the fluid pressure that is near lithostatic. So then later on we have then E in our wavelets here, cassiterite or vein pape. Fluid is still mostly magmatic or mixed with means then with meteoric fluid, yeah? That is just what comes from above. and also a medium salinity. So later on in stage F, that is here close to the boundary of 300 degrees Celsius, you have then parts of feldspar in country rocks. The fluid is mostly meteoric, and the fluid pressure is nearly hydrostatic. So that means that this shows on the example of a tin ore deposit, first where your tin becomes enriched. I mean, it depends on the salinity and on the pH and so on. And which other zones you can form. So, and here in the country rocks, that depends then also on the chemical composition of the country rocks. Yeah, if it is a limestone or an anomosilicate rich rock or whatever you have. So, any questions? Yeah, you must ask, because at the examination it is then too late. But don't be afraid, nobody will score straight. Because you are coming up with this stuff again and again. You know, that was now the example for a tin ore deposit, the mechanism for a gold or copper ore deposit is exactly the same. You have just different chemical parameters. I mean, if you are going to landing and we will show it to you, then you will find these malachite and these are malachite. Yeah, azurite as well. No. But you will find this malachite. Yeah, and you can identify this malachite very easily in the field because it's just lying around. Then you will not look in Navy for a tin ore deposit only by finding its malachite. I mean, the most closest thing that is the copper ore deposit. Yeah. So, and then you are just walking there around with your hammer and taking the rock samples, and then you can identify most of the rock forming minerals very easily. So, and then you can just take one of these textbooks without doing own calculations. You can just take one of these textbooks using these diagrams, and then you can make first rough estimations. So, and if you have done these first rough estimations, then you can make your thin sections from the samples, sending them somewhere for microprobe analysis, and then you can go more in detail. That's the way how it works. And if you can do this, then that is very good. Here another very annoying diagram. So that is just also for the formation of a tin ore deposit, yeah? And here we have the different tin species in the fluid, yeah? We have here the fluid, potassium chloride, and we have divided by HCl in the fluid, and then you have here different species. Here, for example, you have tin chloride, yeah? Here you have some potassium tin chloride, here you have also potassium tin chloride, and these are then just fluid species. they have done this diagram. Yes, in the tin HCl, KCl system at 700 degrees Celsius. So that has now nothing, it's not important for you in the examination because that's too tough. But I will only show you that you have your ore minerals, at least those in the hydrothermal stages, or while you are cooling down your granitic intrusion in your contact metamorphic zone, in this cryosets, in this hydrothermal zone, is strongly dependent on the fluid. So, and that is the important thing for you as an ES301 student. Without fluid, you are doing nothing there. Yeah? So, coming back to our things what I told you before, if you have a fluid-rich intrusion, then it is a more proper environment for rock-forming processes. If the intrusion is very dry or it cools down very fast, that is the next one. If such a melt cools down very fast, then there is no time for any movement of your fluid. Yeah? So, and therefore you will not form any ore deposit. Yeah? So you need always the time factor, the composition of your fluid, the depth of the intrusion, and the temperature. So this we have done. So that is now a more friendly picture, this one here, yeah. Here we have again our granitic intrusion. So and here we are starting with our contact metamorphic zone. And here we have some species in the fluid, that is fluorine, chlorine, bore. And the last one, I cannot identify, but that doesn't matter. For you, it's okay if it is fluorine, chlorine, or bore. These are your fluid species. Then you have here the inner halo that is close to here. And you are forming their different zones. Here you have a mica quartz zone, here you have a quartz zone, and you have a topaz zone. And then you have your outer halos, and then it depends in which kind of country rocks your melt is intruding. Yeah? So that is everywhere here. So and here you have a zone where the outer halo is made up of ultra basic rocks, and their amphibolitization will take place. Yeah. So, and in the zone between, you have then chloridization. You will form talc, biotite, plagioclase, phlogopite, and plagioclase quartz. So that means here in this zone, you will form a different ore deposit compared from this zone. Yeah. I showed you this before as well. Here we have an outer hollow, and the outer hollow contains here carbonate rocks. Then you will start to make here marmoritization or marbles, tourmaline, micas, and fluorite. So, and here we have an outer hollow containing of aluminosilicate rocks. Then you will produce a hornfels, and you will produce the spicels, and you have the hydrothermal stages. In the hydrothermal stages, that is here with sulfides, I showed you this before as well. You have quartzitization, ceritization, and adularization. Adularization, yes. So, and in all these different zones, you are forming then different ore minerals. Yes. Okay, then we are done for today.
Remember, practical is on Monday, 5 for ES301.